Hello folks, welcome back to Merrill Math. I'm Mr. Merrill, and today we're going to be talking about the mean value theorem. This was actually a request I got a while back from one of the viewers, so I apologize that this is coming so late. So it's probably not very useful to you right now, but it's about, I don't know, like close to 3 in the morning right now, and I'm kind of bored, so I felt like doing some math. So the mean value theorem is, well, where we're going to start is this. So I'm guessing that if you're in, I didn't talk about this. It's a calculus topic. So typically first semester Calc AB. So this is where you're in, you're just about knee deep in differentiation. Then they throw the mean value theorem at you. It's something that sounds a lot more complicated than it is. And I know I say that about a lot of the stuff that I talk about on here, but this one is also true. Conceptually, it's very easy to understand. So we're going to talk about this definition, then we're going to talk about the concept, and then hopefully it will make a lot more sense. So I'm going to read through the definition. This is probably similar to something that you've gotten in like classroom notes. So what we're going to do is suppose that a function f is continuous over the closed interval ab and is differentiable on the open interval ab. First off, those are two pretty big assumptions, and when you're using the mean value theorem, you have to be really careful about those first two assumptions. It has to be continuous, and it has to be continuous on the closed interval, and it has to be differentiable on the open interval. So you want to be really careful when you're working through problems, because sometimes they might try to throw curveballs at you on quizzes and tests and stuff. But if those two conditions are met, then there exists a number c in that interval, the open interval ab, such that f prime of c, so the derivative of this function at c, or the slope of the graph at that point, is equal to f of b minus f of a over b minus a. Now this, if it doesn't, it should look familiar. This is the slope formula. So this is y2 minus y1 over x2 minus x1. This is the slope formula. So basically what we're doing is we're finding the slope at these two endpoints. So whatever our graph looks like, let me find something to draw with and on here. So let's say we have some sort of graph, and here's A and here's B. So this point up here is f of b, and this point up here is f of a. And if I connect these two points here with a straight line, reasonably straight, what we get is this slope that we're concerned with. So what we're saying is there is some point, so this is continuous and it's differentiable over the intervals and so on. So what we're saying is there is some point in between here where the slope of the graph matches that. So we kind of look here like, okay, these are too steep. This might be somewhere around here. If we're looking at this, it might be somewhere around here. Looks like the slope of the graph is approximately that. And there appears to be a solution down here as well. So there can be multiple solutions for this depending on the function that you're looking at. So there isn't always just one. There can be 2 or 3 or however many. So it's kind of an interesting thing to look at. When you look at a graph, it seems to make a little bit more sense. But what made this concept really stick in my head when I was going through calculus was, and at the time, like in college, I was doing a lot of driving because I went to college up in Des Moines, but I'm originally from Ottumwa, and that's about 100 miles worth of driving that I would have to do every week to and from. So I spent a lot of time driving and just thinking about stuff. And one of the things that made this topic really stick in my head was thinking about derivatives. A derivative is a slope, but another way to think about a derivative is a rate, or better yet, a speed, like a velocity. Not really a velocity because it has direction and magnitude. Let's think of it as a speed. So a rate of change of a graph, right? So they're saying that this rate of change is equal to the average rate of change over the interval. So if you think about it in terms of like driving in a car, let's say you're driving from, let's say Des Moines, because I'm in Des Moines right now. Let's say we're driving from Des Moines to, I don't know, Kansas City. What is that, like a 3-hour drive? And if you start out going, what's the speed limit? 65, 70? I don't know, the interstate, whatever. At any rate, let's say we start out at 65 and we end the trip at 65. But over the course of the trip, we average, let's say, higher than that. So at the endpoints, where our rate is lower, let's see here. So let's draw a position versus time graph. So we start here at 65, and that's our rate of change, and we end at 65, but our average is somewhere higher than that. So what this is saying is, over the course of this trip, somewhere during the trip, you have to travel exactly your average speed. It doesn't mean you have to be going that the entire time. It just means at some point during the trip, you have to travel at your average speed. So let's say, our rate of travel does something like this. Like we go maybe a little bit faster. This green's having trouble drawing on here. So we go a little bit faster, and then maybe we go a little bit slower, and then maybe we come back up to here, right? So if I were to average these out, it would probably be about 65. So that means at some point we had to travel 65. So at the beginning, and maybe somewhere in here, and then maybe at the end point. So if you can visualize this, thinking about derivatives as rates, that makes this a whole lot simpler. So it's just saying, over the course of this journey, we have to travel the average speed at some point. Because if we never reach the average speed, that means that we're either going higher than the average speed the entire time, which means the average is actually higher. Oh, I bumped the camera. Sorry about that. I get really emphatic, but you can't see it on camera. So if we travel the greater than the average speed the entire time, then we're above average. Then that means the average is actually higher, so we need to adjust it. Or if we go below the average speed the entire time, then the average is too high. We need to adjust it lower. So at any rate, hopefully that makes a little bit of sense. We're going to go through an example here. So where this gets a little bit messy is when we're doing actual problems. The concept isn't too bad, but when we get into the actual problem, some of the things can feel like they're slightly unfamiliar. All of this stuff should feel relatively familiar, but some of it maybe we haven't seen in quite a while. So one of the first things I like to do with a problem like this, okay, so let's start with this. So we've got our function x cubed minus 4x squared minus 5x, and we want to find all the points satisfying the mean value theorem over the interval 2 to 4. Okay, so what I like to do first, and I'm sure I'm going to have to expand onto another sheet of paper here because I didn't give myself a lot of room, is just find the average. So what I want to find is this whole f of b minus f of a over b minus a. What this is the slope formula, y2 minus y1 over x2 minus x1. So we have to do some calculating here. So we want to find f of 4 minus f of 2 over 4 minus 2, which is 2. So f of 4, let's do some calculating here. So we've got, 4 cubed, what is that, 64 minus 4 times, I'm writing off to the side here, you just so I don't fill up room on this page because I'm kind of running out. 4 times 4 squared, so 16, minus 5 times 4, so 20. So I've got 64 minus 64 minus 20, so that's negative 20. And f of 2, so I've got 2 cubed, that's going to be 8, minus 4 times 2 squared, which is 4, minus 5 times 2, which is 10. So what do I have here? 8 minus 16, that's negative 8, minus 10, that's negative 18. So I'm going to say plus 18, because it's minus here, so I got negative 18 over 2. So what do we have here? So negative 2 over 2, that's negative 1. So this is an important part. So this is, if we're thinking about the car example, this is our average speed. So at some point over this graph on this interval, we have to be going this speed, or we have to reach this slope at some point. So now we get to the fun stuff. That's the algebra part. Now we get to do some calculus here. So our function, f of x, is x cubed minus 4x squared minus 5x. What we want to do is find f prime of x. So we need to do some power rule stuff. So this isn't too bad. So the 3 comes out front. I've got x squared. 2 times 4, that's going to be 8. And that's going to be just x to the first minus 5. Okay. So this is our derivative. So this is how we can find the slope of our graph. I keep bumping into stuff this time. I'm fidgety for some reason. Okay, so sorry about the earthquake. What do we have? Okay, so here's our function. Here's our derivative. Let me make sure I did all that right. Okay, looks good to me. So this is our derivative. This slope at some point needs to be equal to negative 1. So if we have this case here, we can add 1 to this side. So what this is saying is 3x squared minus 8x minus 4 is equal to 0. Now this, again, is another situation where we might be unsure of how to proceed. This is just a quadratic. We've been solving quadratic stuff since, I don't know, Algebra 1. So we can just use quadratic formula. So hopefully you remember that. So x is equal to, what do we have? Negative b. So what's that going to be? 8 plus or minus square root b squared 64 minus 4 times a, which is 3, times c, which is negative 4, over 2 times a, which is 3. Okay, so now we just have to do some cleaning up. So x is equal to 8 plus or minus 4 times 3 times negative 4. What is that? 16 times 3, that's 48. So negative 48. So 64 plus 48. Oh, geez. 64 plus 48. So 60 plus 40 is 100. 4 plus 8, so 112. Over 6. So far, so good. I think we're on the right track. Yeah, I think so. Okay, so what do we have to do here? So that's 80, 96, 112. I think 16 goes into this. So we're going to do some factoring here. So x is equal to 8 plus or minus, this is 16 times 5, 6, 7. So we're going to have 4 radical 7 over 6. So we get 2 answers for this. But what ends up happening, and I don't have my calculator handy. So one of these is about 3.10, and another one is approximately negative 0.43. I'm cheating because I'm not doing these on my calculator, but that's okay. So you can do these calculations on your calculator and get these values for this. Okay, so this isn't quite the answer. So what we're looking for, if we go back to the original problem, we want to find all points satisfying the mean value theorem over this interval from 2 to 4. This doesn't satisfy it. The 3.1 does, because 3.1 is in between 2 and 4. So this is the one we're looking for. So what our answer is going to be is, what is this, 8 plus 4 radical 7 over 6, which we can simplify a little bit. We can factor a 2 out of everything. So 4 plus 2 radical 7 over 3. And that's it. So the mean value theorem isn't as bad as it seems. So what we have to start with is a little bit of slope formula. That's algebra 1. We have to take a derivative, and then we have to set that equal to our slope. And then depending on what this derivative ends up looking like, if it's just a quadratic, we can use quadratic formula, but then we just have to solve it. So depending on what this looks like, we can use different methods for solving this part. But, you know, beginning derivative stuff, they'll probably throw a lot of these quadratic things at you. So anyways, we got 4 radical 2, or 4 plus 2 radical 7 over 3, or approximately 3.1. So if you have any questions or comments, you can leave those in the comment section below. Otherwise, thanks for watching. Oh, okay. I was... It's just a long silence. Okay, well, anyways. Alright, 3, 2, 1. Hello, folks. Welcome back to Merrill Math. I'm Mr. Merrill,